going to try and do today is take you through 3 real-life examples of trying to follow a mineral system. I'll try and be as geological as possible while I'm doing it. And they're very different examples, and therefore I use very different techniques for each. And it's just to get you thinking on how one can reduce the size of the haystack in some indication, in some areas. And in others use structural interpretations to infer targets rather than look for bumps. So it's no longer enough to use geophysics purely for bump detection. We need to use it far more intelligently, and we need to be able to map the geology, the structure, and the alteration as accurately as possible, often undercover. So I'm going to cover the use of Airborne EM, gravity and mag. I'm probably not going to get to AMT because I put in too many examples, but I will do the ground gravity. So in this first example, which is in Mozambique, I'd like to acknowledge Rovuma resources and African rainbow minerals for allowing me to show this. They've asked that I take all the location data off, so don't ask me for any of that. So here we are, we're in the middle of in Mozambique here, and interested in prospecting this mafic, ultramafic rock here for sulfide deposits, massive volcanogenic massive sulfides, and possibly other things. But the trouble is it's a hell of a huge haystack. This is 270 kilometers long, this gabbroic or mafic rock over here. And it's been very poorly mapped because it's in a very remote part of the world. So one of the first things to do is to do some decent geological mapping and then to try and reduce the size of the haystack to look at a much smaller area for the mineral system that we're after. Total field magnetics, this area is beautiful. You can see the geology very, very nicely, and it's a pleasure to map. The radiometrics ternary is an absolute mind-bender as far as I'm concerned. This is a geological map in itself. Clearly there's no cover here, so we're not into the zone where we're talking about undercover yet. And essentially that is a geological map. You just have to assign names to these units. What is intriguing is that this ultramafic or mafic rock here and this one appear to have once been the same body all the way along there, and they've been sheared apart. And there's been an amazing rotation on this particular chunk of it over there. And it's been clearly separated into quite an actively sheared area, and one that is still quite homogeneous. So it's our first clue. When I put the total count radiometrics on and I start interpreting big shears, this is what it looks like. Very easy to map, as I said. There's country rock on either side, and this is what we're interested in. And I must say that they have this interpretation of this rock in that it's an ocean floor. This is actually an ophiolitic chunk of rock, and that somewhere in here we have a spreading center, and it looks suspiciously like it may be along here because of this shear. This may be the major structure. Interpretation of major geological elements are very easy. Put all the ultramafic rocks in. This is actually granulite facies that's been extremely metamorphosed. It's in the Mozambique orogeny. And all the way along there where we had that very blue radiometric signature, and around this side we have a graphitic schist which wraps around there and gives us a sense of rotation of that block. And we also have some magnetic units in black. I've mapped in all the magnetic units within this conductive schist because we do have some conductivity measurements as well, and we do have some EM surveys. So this becomes interesting, particularly this highly sheared part of the granulite. Geological interpretation, when it's finished, looks quite complex, and we've managed to divide it up into a whole bunch of exploration blocks. But the whole time we were doing this, Rovuma have been at it, taking soil samples and mapping this in large areas here. And all the geochemists in the room will become squeamish to know that they analysed every single one of their samples with a portable XRF. I've never seen the inside of a laboratory. Their attitude was, this is going to get us into the right ballpark. We don't care about the exact number, we just want to know there's a copper anomaly in an area or a zinc anomaly in an area. So we started. By the time this interpretation was done, they had done quite a bit of groundwork, for 5 years in fact. And what was really interesting was this chemical sediment coming out in this zone over here. This is a manganese or a gondite, and is often associated, or they have associated with, the actual spreading center on the ocean floor. When I put in all the geochemical anomalies they got from the XRF work, and they've been given names, it became quite interesting to me that there was this very magnetic belt in between these two shears, or graphitic schist units. Sorry. And all of these appear to be, all of their geochemical anomalies appear to be lying in this magnetic zone between these two. So is there an association with the chemical sediments? And secondly, what is this very magnetic unit that goes through here? And what I've done is, for this stage, I've interpreted it as a high strain zone, whereupon all of these are shears, and we've had hydrothermal magnetite or alteration, information in this zone here. Many of the geochemical anomalies appear to be coming out of it. So essentially what I managed to do here, or what we managed to do, is reduce the size of that huge area to something much smaller. This is now being tens of kilometers instead of hundreds of kilometers across. If I plot in that high strain corridor in orange, and I'll keep my graphic schists on, it becomes patently obvious that there is some sort of linear relationship, and that if we look for other high strain zones on the same trend, we may be barking up the correct tree, and also mapping out other high strain zones, these blue ones here. So there are a number of high strain zones, and the question now becomes, which of these are of interest? Obviously, this could become a target area, and we might want to follow down into these zones here. So this is just one example of a large mineralized system, a footprint of a large mineralized system that, by inference, using structure and some groundwork and some geochemistry, we've managed to reduce to, should I say, a hotspot, a corridor that is worth following, and is an overall, as far as we're concerned, the overall footprint of the mineralized system. I'm going to get back to an undercover example. So that's using superficial geology. Quite an easy example because everything's on surface and the geophysics is fantastic to use for mapping. Now we're back to First Quantum's project that Steve talked about in northwest Botswana over here, which is under Kalahari cover. I did show quite a lot of these slides yesterday, so I'm not sure how many of you were in that talk, but I'm going to have to show just a few again to bring you up to speed before I start moving into our interpretation of the gravity for the basement architecture. So here we are here, we're looking at Katangan rocks, the Zambian copper belt curving here, around here underneath the Kalahari and popping out here in northwest Botswana, and this is the project area. Again, this is the Tradilo Hills that I mentioned yesterday and that Steve actually showed. This is outcropping sandstone and it's been interpreted as lower Rhone. It's the only rock outcropping in this otherwise very sandy desert. Kalahari cover, it's very, very flat. It's a desert, less than 200 millimeters of rain. And this is the thicknesses of the Kalahari sand in all of these countries. This being Botswana, there's northwest Botswana, and we're right on the fringe of a really thick trough of Kalahari sand. And there's much thicker and larger troughs up in Angola. But for now, we just need to know that we're in an area right on the fringe with some really thick stuff that we can see through. And again, if we look at the SRTM, for that area, there's the Tradilo Hills, only outcrop in the area, everything else incredibly flat. These are dunes, dune relics, and this is the panhandle of the Okavango Delta, so we're right on the western edge of the panhandle, and this is Caprivi Strip, and this is Namibia. Aeromagnetic data, banded iron formation is showing up very, very strongly. It wasn't originally mapped on the geological map of this area because it was just an interpretive map. And this is what brought Sodilo into the picture. They were looking at kimberlites, but they were also looking at the iron ore associated with this potential iron ore deposit. And we have all these magnetic units, which are probably shales with some pyrrhotite in them. What we really want to do is map beneath this Kalahari. We want to map those shales because we're interested in the Katangan stratigraphy, shale-rich Katangan stratigraphy, as I said yesterday. So we flew that whole area with spectrum. And again, I've got a late tau map here, and all of these conductive units have popped out in the area of interest. The banded iron formations are right here. So what we're looking at is conductive units, and this is Kalahari, which we have not managed to penetrate with the spectrum system. So we believe we've penetrated up to about 80 meters, maybe 100 meters at best, and then after that, we're not getting through to the basement geology. This is all sand that we've not managed to see through. So that kind of reduces the area of interest and of this mineral system to that area there. Prospecting philosophy, as I said yesterday, most conductive units in the spectrum EM survey are the graphitic shales, which lie beneath the sand, and they're the target host for copper mineralization. The shale unit closest to the basement is the most likely to host that copper mineralization. That's what we've been using as our prospecting methodology there, but it's obviously there's still a big area and there's lots of shales. And the reason why we say that is because we believe that the brines carrying the copper come out of the basement, and that this will be the first reducing unit which will pull that copper out of solution. So if you look at a classic copper belt stratigraphic column, this is down here in the lower Rhone is where one normally associates copper belt deposits. But what's happening is in the upper Rhone, and particularly in the Moasha over here, we have these carbonate and shale-rich lithologies. There is Sentinel Mine, which is associated with the Moasha shale, and it's quite graphitic. And if you follow this across all the way from the DRC, and we go through the domes region of Zambia, central Zambia, and we come out in Botswana, we've got a lot more ironstone associated with the graphitic shales, or the black shales, but they are there indeed. So we believe it's a correlative, we're not 100% sure, but we believe it's a correlative of the Moasha shale that we're interested in. And we're going to be interested in where the shale lies close to the basement. Basement stratigraphy, won't go into too much detail, but there are lots of geologists in the room, so they're probably happy to see some core. It's granite, a little bit of gneiss. It's been dated at 2.6, so it's Archean. And this is, we don't often drill into this rock because we never go through the sediments into it, but this is what we're interested in. This is what we want to get very close to because we believe will be the source of the copper. Moasha shale, on top of that, is graphitic. It's variably conatiferous in places, so it's metamorphosed, where originally we believe shales and siltstones, and contains quite a lot of pyrrhotite, so it has a remnant signature, and it is pretty conductive, but it's variably graphitic. It's not always extremely conductive, depends on where you are on the strat, and it becomes more carbonate-rich down section. So it's associated with carbonates. When you do a ternary image of the late tau, the mid tau, and the early time channel tau from the spectrum data using RGB, you get a very impressive image which shows all of the most conductive units in bright red, all the Kalahari cover in this creamy color, and it actually sits like a blanket over the top of these shales over here. Where we're seeing clean through into the black is very, very resistive. So it's either carbonates or it's resistive basement. We've got it there and we've got it there, and these strange sinuous conductive units, which are not as conductive as those, in this case are paleochannels. They're Karoo paleochannels lying underneath the Kalahari, and they're filled with conductive Karoo sediments. Here's the Tsodila Hills, very resistive of course, being sandstone, and the dominant wind direction is to the east, and we believe that the greater thickness of Kalahari sand is banked up behind the Tsodila Hills at that basement high, and that outcropping sandstone. In our interpretation of the black shales and all of these structures, I am kind of rushing through this because I showed it yesterday, and I'm sure a lot of people saw it. What we do then is we start targeting which shales lie closest to basement. These become target areas to perhaps look at on a grand scale. This is the mineralizing system, or the potentially mineralized system, but now we need some way of focusing in, and we need to know a lot more about the basement. So we decided in order to learn more about the basement, we're going to have to do an airborne gravity survey. Before we get into that, I just want to show you the mapping we did. Just putting shale units in, folded shale units on top of conductors. We draw a strat line through there. This is the stratigraphy from the strat line. Those are all of the holes. And this is really just drilling, not to find mineralization, but to understand what are we in here. What kind of stratigraphy are we in? So we have basement or pseudo-basement, a proxy, sometimes a schist, a biotite schist, biotite called schist. We have these diamectites, very thick layer of diamectite, unusually thick for the Moasha. Usually the ground conglomerate is quite a thin unit, but it does have magnetite-rich shales around these banded irons, which are sitting in the middle. The banded irons are heavily contorted, they're very folded, and then we have another diamectite on top of the shale and carbonate unit, which is a bit strange. You have to either infer that that's a new diamectite unit, and that younging is that way, or this whole thing has been folded over. What we're looking at is a refolded recumbent fault. And over here we have some calcareous sandstones which are quite resistive in the EM and are possibly higher up in the sequence, like lower Kundalini, but we're not sure at the moment. So in order to learn more about the geology, and particularly about the mineral system, because the mineral system is being defined by structures probably in the basement, and by the basement topography, we decided we needed to fly this area with airborne gravity, because this area has now become our area of interest. We have all the shales and we have the banded iron. So this is the shape of the gravity survey. There, the Chavila Hills. And using our petrophysics, we did quite a number of readings. We've got quite a big database. We looked at a density comparison. Okay. Whoever that is owes me a beer. This is our basement.
It was for you.
Shut up. What is quite interesting is that the basement is coming out. The few samples of basement that we have, granite and quartz-biotite schist epoxy, at 2.6 grams per cc, and every other rock in the area that we measured is quite a bit denser than that. Obviously the banded iron formations are very dense, they're around like it's 3.7. Even our diamictites and some of our fullites are around about the 2.8 mark. And that is what we were aiming to try and do with the gravity, is to show where we have low density areas to map out basement and to map out the basement topography. Because understanding that architecture is understanding the ore-forming system. There's a good example of a density log that went down one of the holes. This is the density probe that we load down there. Where we're in granite, we straight on the 2.6 line, the banded iron formation much denser, and the diamictite above that is definitely denser. So we have this situation where if we have sediments, we're going to have density highs, and we're going to have gravity highs, shall I say. And where we have granite close to surface, we're going to have lows. It becomes very important. This is the final Bouguer data set from the gravity survey. We didn't do the entire spectrum survey, we just did the area of interest. They're the Chadilo Hills, to locate yourself. And what we do have is a strong, almost northerly trending or north-northwest trending gravity low in the middle here, which we have interpreted as a basement high. We have sediments banked up on the side of this basement high, along the contact approximately there, and we have sediments on this flank as well. So it looks like a horst block of basement, which may or may not have, probably does have shallow sediments or thin sediments on top of it, but it's there nonetheless, and it's going to be important to understand that. But of course we've got the Kalahari topography to take into account when you do a gravity survey. So what we did was, with the use of Voxy and some Geosoft software, we managed to take the thickness of Kalahari cover with its density, which we know because we've logged through it, approximately 2 grams per cc, and this paleo channel, and we create the gravity that would be the gravity response for that, and we subtract it from our Bouguer gravity. So in other words, we're stripping off the Kalahari cover and that topography, which is what Steve was talking about. You need to understand what's directly beneath your cover. You don't need to hate your cover, but you do need to understand what's directly beneath it. And when we've done that, we're left with what looks like a contact approximately there between the basement high sediments, a basement high sediments, and this is where all of our graphitic schists or black shales have been mapped. We do have the complicating fact that where we have banded iron formation, it's very dense, and that is superimposed on this basement high. We believe those banded iron formations are lying in a thin layer above the basement, and therefore we do get a sort of an anomalous area here with a strong gravity high, where it's on top of the basement horst block. And then we have these other areas where it looks like we have sediments on top of the basement as well. So I did a quick forward model, or a quick model across there, just to see if we could make something sensible out of this, knowing the exact densities that we're dealing with. And you can very easily get that kind of gravity response by having a low density basement horst block and a thin veneer of sediments on top of it, and then thick banks of sediments on either side of that horst block. And interestingly, when you start looking at a residual gravity image, some interesting things start popping out. You seem to have, you can put in these linear structures, this being the edge of the horst, but the edge appears to be offset by brittle fractures, almost northerly trending, which are corroborated in the geology that we've interpreted from the magnetics and the EM, and various other corners that match quite well with the geology. I'm going to show that to you now. And my inference, this would be an up-thrown block of basement. This would be a down-thrown block. That would be down-thrown. All the gravity highs, the down-thrown blocks are filled with sediment. They've got a thin veneer of sediment on them, so they become weak gravity highs. This would be a very shallow piece of basement, and then we'd have sediments in all these areas here as well. So what it looks like we've got is a main basement horst, and then it's got micro-grabens in it, and it's been faulted. Kind of like this. This is just a cartoon that I sketched up. This is the overall basement horst from there to there. We've got dense sediments banking up, possibly thrusted or onlapping onto this flank. We know we've got the Tudela Hills and those sandstones over here. Not quite sure how they fit in, but it's obviously quite thick. There's a very strong indication that there's a fault here where these sandstones are. And all that Kalahari sediment is filled up that fault, on the down-thrown side. So we have these basement horst blocks, and they've got micro-grabens in them that have got thin bits of sediment in them, and then this whole thing is offset by what look like brittle fractures. So we're starting to get a handle on where our big structures are, and where there's some offsetting smaller structures, and therefore, if you start to get a handle on that, you must be getting a handle on the mineralizing system. Okay, that was a cartoon. Now when we overlay it on real geology and real magnetic interpretations, you see some areas where there's a hell of a good correspondence. We've interpreted basement highs as the dotted and a graben as a much coarser dot. So where you see, and this ties in with the actual geology interpretation, and some of these corners are very, very clear faults in the magnetics. So what we've done is managed to try and honor the magnetics at the same time, plus the interpreted geology, plus the EM, and come up with quite a complex horst block that is faulted in numerous directions, but where sediments are preserved in some of the down-thrown areas, or some of the micro-grabens. And here's a slide showing that. We have that spectrum resistor and that spectrum resistor there that we talked about earlier. Some of this is nicely explained. We had a termination in this conductive black shale over here. It was very difficult to understand where the heck that thing went. Now we've got a fault and we've got a basement high over here. Suddenly we could start explaining terminated conductive lithologies. And the same thing there, where that conductor terminates, it terminates against basement. That's what we're now starting to understand. Previously we just had a conductor that disappeared into nowhere, and you had to try and invoke a fault, which didn't work because there was no corresponding conductor and to pick up the other side of the fault. Or you had to have very, very tight folding and bring it back around again, which wasn't actually hanging together very well, particularly because we drilled quite a few of these. So this is the complex model we've come up with, but it's starting to hang together. And we're getting geology matching magnetics, matching the gravity, and matching the EM and some of the drilling. There are some problems. Down here we haven't got, even though this is supposed to be a down-thrown block, where are our conductors and where is our BIF down there? Some things we still have to sort out, of course. Nothing is ever simple. But some of the faults explain very nicely these paleo channels. This is where the major faults are. There's the Tudela Hills. We're referring a really big fault here. And then Kalahari sediments filling up on the east side of that big down throw. And on the west side, obviously, we've got the Tudela Hills actually outcropping. And then we've got major east-west trending structures which terminate these paleo channels as well. So that fault there would come through there and terminate the sky. It's actually, they were actually controlling these paleo channels. So if I had to just draw the edge of that base, that horst onto our interpreted EM and the shales, what we're saying is that right over here we've got a very strong fault. This is the edge of the graben, sorry, the edge of the horst, and then all these sediments have been pushed up onto the side of the horst. There's probably big shears separating these shale packages, so they're duplicated, they're heavily folded, and then you get a duplication, and you get a duplication, which explains why we have so many shales there. And we've got this overprinting effect of the Kalahari and these paleo channels, but all in all, apart from the banded iron formation area, which is dense, it kind of matches up. We've got sediments that are dense and conductive on that side, and they're shoving up onto this this horst. If I do an inversion of that gravity, and this is an unconstrained inversion, just see what I get, and then I clip it such that I can see basement. So basically I'm saying, what does my basement look like? You do see that very strong fault, and everything you see here is basement high, and then we have these micro-grabens which have been filled up by sediment there. And if you look at that in section across there, basically getting the sediments there and the sediments there, they're dense, and then you get all of this blue stuff is the main horst block, and it's got these minor little down-thrown micro-grabens that are filled with sediments like that. So that's what it looks like in profile across there. Chunks of heavy sediments, big thickness of the heavy sediments, horst block, and then minor faults. But this is the big fault, and this is the big fault here. And that's what it looks like. So what does that look like when I actually overlay it on my interpretation and my geology that we have today? Some of it hangs together beautifully. There's the hockey stick, which is that terminated black shale, and suddenly it onlaps onto a basement high. Areas that don't hang together too well, we know this is basement, we're pretty sure this is basement, and we've got the conductors all the way around it. But here I've got basement sticking out of it. So some of these, because it was an unconstrained inversion at this stage, some of it needs a bit of work. But the next step is obviously to constrain this with all of the drilling and come up with the best model. And we're building this into a 3D block model at the moment. So that's how we've used an airborne gravity survey to try and understand the basement architecture and therefore understand the mineralizing system in that block. And we're using the EM to tell us which are probably the most are the reducing lithologies and where they're closest to that basement block, and we know where the major structures are now. Hopefully they brought up the mineralizing fluids. So it's a big picture, and it's not bump hunting at any stage. What we're really trying to do is build a 3D geological model. How am I doing? 5 minutes.
Keep going.
Sure. So the third example, and this will be quick, is the Kipushi project in Zambia, which is the first quantum project. What we have is a very detailed magnetic survey there in Zambia. And on the DRC side is this well-known deposit, Kipushi, which is a very small, it's a very high-grade zinc deposit. It's kind of plunging steeply, and it's got a very small footprint. It's only 300 meters by 100 meter across. And of course, the target is to try and find more Kipushis in Zambia, because that's where we're working. We're not working in the DRC at the moment, so the idea is what is controlling, was to look at what controls Kipushi and what sort of a deposit is it, and can we look for Kipushis on this side of the border in Zambia. If you look at where Kipushi lies on the geology, it lies on the edge of this pink unit here, which is what we believe to be very important heterogeneous breccia. All the blues are carbonates, all the browns are shales, but what's really important here is this breccia, and Kipushi appears to lie at the faulted contact of the breccia, in contact with shale and carbonate, but right on the edge, and interestingly, right on a corner of the breccia. This breccia is huge, it runs for tens of kilometers, and this is the mineral system we're interested in. We're interested in the breccia, because that's the model we follow. So again, we're not going to hunt bumps, we're going to see if we can map out the mineralizing system. If I just look at the mag, it's not really helping me. That's what the outline of the breccia looks like, and we have some amazing structure, and we have some incredible fold interference patterns here, but I'm not really seeing the edge of my breccia in the magnetics. I look at the EM, the survey that we have there. There is an anomaly over here, but there are numerous big anomalies in late times, and we're not quite sure what these are. But we don't believe that something that size is, you can see that this portion of the breccia is not magnetic. We only have a little bit of it to go on there. And we're not sure what that big anomaly is, but there are several other big anomalies. This is the geochem in the area. Sorry, it's very old, so we only have a scan. There is a big copper anomaly downwind of Kipushi, or close to Kipushi, and it's on this breccia. There are numerous other copper anomalies for following up, but there's some belief that this, because Kipushi is an operating mine, and we're downwind of it, and we're downstream of it, and things like that, that this could be a transported copper anomaly from it. And obviously, if you could get into the DRC on this side, you would continue to do geochem. But again, we're not 100% convinced that that is going to map out the entire breccia for us. But what we did do was some ground gravity, and that has given us an absolutely remarkable result for mapping the contact to the breccia. You can correct the contact to the breccia over here. It's very low density, and it's high resolution ground data, 100-meter grid. These are carbonates, very, very dense, and mapping them out beautifully. We've got a lovely fold around there, onto the top of the breccia. And these corners in the breccia, which the gravity is mapping, are again very interesting to us. We know that Kipushi is a faulted contact. There is a strong fault through here, and there's a second one approximately there. And these faulted contacts in the sharp corners of the breccia become kind of interesting. And now that we know that we've got something that can trace the mineralizing system, which is this breccia over tens of kilometers, we can follow this back down to where we think it curves back into Zambia. We're not going into the DRC. I don't know if any of you know First Quantum's history, but they're not going back into the DRC anytime soon. So they want to find where this breccia comes back into Zambia. And lo and behold, quite far to the south, by extending the gravity surveys down along the border, we've picked up the breccia and it's coming in here, and we're getting some very sharp corners and some very interesting geometries which look faulted as well, and we can start saying maybe there's some drill targets in here. So this breccia is the mineralizing system, and in this case we've managed to map the mineralizing system with gravity, being high resolution ground gravity. And I think I'm going to leave it there because that is my time. Thank you very much. All is clear as mud.
Hey, you satisfied all the questions?
Excellent.
It's clear. That's good. All right.
Yep.
Thanks, Gavin. Great.